Action. So today, we're going to talk about rates of change. I've already talked about that. And we're going to talk about something called the derivative. So I'd like to get us working on this. And we're going to start by talking about what's called the slope of secant lines. And like I said, this is a little different from what the book does. We're going to take the approach that's taken in your book in the section 2.3 project. I love that project. Actually, I have to say something about the book. I like almost all of the projects that are in the book. There's some really nice thinking and mathematics that goes on. And let me just say, you guys know that you're supposed to give a presentation at some point this semester? You guys remember that? Part of the syllabus? It's like 20 points. You guys are welcome to start signing up for that now, in all honesty. As you're doing your homework, if you look at any of these section projects and you say, hey, I could talk about that, I'm going to get it out of the way now. You guys are welcome to do that. I'll give you time at the beginning of class. Instead of doing a homework problem, we'll listen to somebody's presentation. Remember, you're allowed to work with a partner, okay? As long as each person is talking for 5 minutes. And these have enough that you could talk for 5 to 10 minutes each on one of these projects, okay? But I'm going to go through this section 2.3 project with you, or at least the approach that it takes right now, because I think that this is just really good. So have you seen that formula up there on the screen before? Yeah, that's what we did in chapter 1, right? The slope of a secant line is what we're talking about. Today, we're going to be talking about not the slope of a secant line, but the slope of a tangent line. Hey, wait a minute. Isn't that the same formula? Take a look carefully. Almost. What's the only difference?
The limit.
We have a limit. And that's why we studied limits for 2 sections. Okay? The first 2 weeks of the course, we talk about limits because now we're going to apply what we learned. We're going to take a limit and we'll be moving from the slope of a secant line to the slope of a tangent line. And I guess I really should draw a picture for you, because sometimes pictures say more than words. So let me move to the screen here where I can do that. Get my paper out and see what I can do for you. Oh, let's rotate. Why not? Otherwise you get a crimped neck. Okay. So I have some function. I don't know what it is, right? Matter of fact, I'll tell you what it is. See this function? You guys know what this represents? This is the number of unemployed Irish. Well, actually, this part's not, right? So this is the number of unemployed Irish. It's been increasing, right? And actually, I could give you some actual values if I had my calculator ready. Who has in their calculator ready to go? I saw it. That was a beautiful. Can I have it? Thank you. So let's punch this up here. I just want some actual numbers. I mean, here's all kinds of stuff on the window. But what I want is I want some good old data. So here's the y equals. There's the function. She typed it in with parentheses. That's one of the keys, right? And now I want to go back to the graph, and I want to calculate some of these things. So I'm going to hit second calculate a value when x is 0. And so what does this mean? It says 105. So we have the point 0 and 105.36. That means what? If you had to interpret that. In 2000, there were, what? 105,000 unemployed. Okay. And then let me talk about in the year 2010. So if I want to know that, I can hit second calculate a value, and I'll plug in 10. Oh, wait, something's wrong. Why did that happen? Because I remember the reasonable domain. Didn't you guys tell me the asymptote was at 11.6? Let me check that out. We did 0.35 divided by 0.03, 11.6.
Yeah, what's wrong with this? It went from 105 to 120.
Let me see that again. So it can calculate a value 10. It says negative 120, and it's down here. I feel like my I feel like my asymptote's not in the right place here. Did you get a positive 120.8?
Yeah.
Formula typed in right?
That's what I'm going to check next. Let's see. We have plus 26.34. What do you have? Oh, 2.5. Let's make that a 3.5, and then we'll fix it. Okay, cool. So we're going to redraw, and now my asymptote is going to be where I thought it was, around 11.6. Okay, so let's try that again. Second, calculate a value of 10, 120.8. Let me just do second, calculate a value. Well, that'll be it. Okay. So over here, we have 10, and we have 120.8, right? So let me ask you, do we have more unemployed or less unemployed? We have more unemployed, right? Now, if I wanted to, matter of fact, would you say that the number of unemployed has been increasing for that entire 10-year period? Has it been increasing for the entire 10-year period? From the picture, it looks like it, right? I mean, all I'm really doing, if I can kind of redraw it again, is I'm talking about this kind of a picture, right? 0, 105, and then 10, and almost 121, right? That's the picture. It's been increasing. Now, you see that line there? That's called a secant line. A secant line is, by definition, a line that intersects 2 points of a curve. So I could compute that slope. I could compute that slope. But maybe here's the question that I want to ask. Well, actually, let's do that. Let's compute the slope. You guys did this in Chapter 1. The slope of the secant line would be, let me go ahead and do it in red. Well, basically, it's 120.8, because that's what that said, minus 105 point, let's call it 4, over 10 minus 0. And so I get, well, I get 5.4 over 10, so I'm getting about 0.54, right? What are the units for that slope? Oh, no, not 0.54. 15.4. So I get 1.54. 1.54, but my question again is, what are the units? 1.54 what?
Jobs lost per year.
Yeah. Thousands unemployed per year. That's the rate of change. That's what we called AROC. AROC is the average rate of change. Well, today, what I'm going to try to compute is what I like to call IROC, instantaneous rate of change. The problem I'm going to ask today is, how fast, let's put it this way, how many jobs were being lost per year? What was the rate of change in the year 2010? See, in the year 2010, I'm like this. Oh, I can't see that, sorry. In the year 2010, jobs are being lost. Let me ask you this. I did the problem going from year 2000 to year 2010. If I were to do the same problem starting in the year 2005, so 5 whatever it is to 10, that would be this secant line. I could compute the slope. I'd get a number of jobs lost per year. Let me ask you this. If I did the black line, would the answer be greater than or less than what I did when I did the red one? Definitely. It's more steep, right? Or you could say I'm only dividing by 5. I'm not dividing by 10. You guys with me? It's going to be greater. Well, if you want to know what we call an instantaneous rate of change, what you do is you compute the slope of these secant lines, but we move the point closer and closer towards 10. You know, I could do from 9.9 to 10. And then eventually, what I would get is this kind of a picture where you're just touching the curve. And that's not a secant line anymore. That's what we call the slope of the tangent line. So a tangent line intersects the curve in one point. The tangent line intersects the curve in just one point. But in order to do that, see, you can't compute a slope anymore, right? Because what's the formula for slope? Isn't it y2 minus y1 over x2 minus x1? But what we do is we take a limit as x approaches c. We use the same formula, but take a limit, and we're able to compute it. Okay? So I want to give you an example. Now, here's an example. Let's take the function 4x minus x squared. I'm going to give you a value for c. c equals 1. And I'm going to go ahead and try to do a computation here.
What does C stand for? Does it matter? Or?
Well, yeah, it does. C is going to be the point of tangency, the x-coordinate of the point of tangency. On my picture, here, let me do this. 4x minus x squared. Let's draw a picture with a calculator, first of all. We have it, may as well use it. So this is not applied at all. This is just me, trying to teach a little calculus. 4x minus x squared. And I'm going to hit zoom standard so that I have just my normal graph paper from -10 to +10. And there's my picture. Actually, that's like what we did the first week also. What shape is that? A parabola. We see that a lot. I knew that would happen. It's degree 2. Okay? So I want to take that picture and I want to think about what I can say about that. I mean, f of x equals 4x minus x squared. By the way, if you factor that, you get x times 4 minus x. You could see that not only does it go through the point 0, 0, it also goes through the point what?
4, 0?
4, 0, right? It's a parabola. It has some symmetry. where's the axis of symmetry going to be? Sure, at 2. And if you plug in a 2, 8 minus 4 is 4. You'll see it goes through the point 2 comma 4. Now I still haven't drawn C. That was what you asked me about. What's C? C equals 1. So that's the number I want to approach. Okay? So when C equals 1, by the way, if you plug in a 1, you get 4 minus 1 is 3. 1 comma 3. You guys with me? By the way, I could compute some different slopes here. Right? See this red line here? That slope would be 1. Because that's 4 minus 3, the y-coordinates, over 2 minus 1. See this slope here? Talk to someone next to you about what you think the slope of the blue line is. No telepathy allowed. You have to talk. Talk to the person next to you about what you think the slope of the blue line would be. From 0, 0 to 1 comma 3. That's much better. Telepathy. You guys are cheap. You got 3 minus 0 over 1 minus 0. Did you get 3 for that slope? All right. So now let me explain what we're doing. Both of those slopes I computed were slopes of what are called secant lines, because they intersect 2 points. What I'm trying to compute in this problem is the slope of the tangent line, where it just hits the 1 point and just kisses the curve. The Latin dance called the tango, you're just touching. That's where it comes from. Tangent, tango. I took Latin. All right, anyways. But here we are, right? We want to know the slope of that line. Hey, I would bet you something. I'm going to bet it's bigger than 1, because it looks steeper than 1. And I'm going to bet it's not quite as steep as 3, because it doesn't look that steep. What do you think it is? You don't think I would do that, do you? Design the problem. Well, we'll see. All right, anyways, let's see what happens. So how do we compute it? Well, we're going to use our formula. So what's my formula? There it is. We have to compute a limit. So let me go ahead and do that. My limit, let me write down that same formula that I have here. I'm going to try and use it now. So M tan is equal to the limit as x approaches. Now it says C. What am I going to write where it says C? 1. Of f of x minus f of 1 over x minus 1. I put a 1 everywhere that I saw a C. Now that's equal to the limit as x approaches 1. Here's the thing, guys. For this problem, I told you what f of x is. What is it? Well, it's up there above, right? Oh, you can't see it now. Let me write it. There it is. 4x minus x squared. Right? That's what f of x is. Minus. Now, f of 1, do we know what that is?
3.
That's 3. So we're going to subtract 3 over x minus 1. Hey, by the way, if you were to plug in a 1 right now for x, what would happen?
It would exist
Why do you say that?
because the denominator would be 0.
How many agree the denominator would be 0 at that point? But what would the numerator be if you plugged in a 1 right now?
0.
4 minus 1 minus 3. What would you get? 0 over 0 is what we called indeterminate. What did that mean? It means we have hope. Maybe we can do something like factoring. Yeah, let's try some factoring. All right, so maybe this limit does exist. Let's hope so, or I just wasted 15 minutes of our time trying to compute it, right? I only have so much class time. All right, so let's see. This is the limit as x approaches 1. You told me to factor that numerator. Let me factor out a negative sign. What would be left if I take out the negative 1? I think I see it says x squared, because it was negative x squared. And then wouldn't it be minus 4x? And then it would be what?
Why would it be minus 4x?
Well, it was positive 4x, but I'm factoring out a negative. See that?
Mhm.
And then what am I going to put here? Plus 3, because it was minus 3. Do you guys follow that?
Yeah, I still don't know how to.
Oh, I know you don't know why. Well, you told me to factor. And for me, factoring, I don't like starting with a negative. I like to put it in this form. Maybe you'll see now. The limit as x approaches 1, we have a negative sign. How do you factor a trinomial? Usually it factors into 2 binomials. Does that work here? What do you get? X minus 3 and x minus 1. Was that a good thing? It was, because what can we do now? Cancel the x minus 1s. I'm getting excited. I'm getting the limit as x approaches 1 of negative, just x minus 3, right? Everything else canceled. If I plug a 1 in there, I'll get negative 1 minus 3. So that's negative negative 2. What's it equal? You guys guessed right. Ha! The slope is 2. But maybe what's more important is we understand why we're learning about limits. If you want to compute an instantaneous rate of change, what you have to do is you have to compute a limit. Okay? And that's where we're headed here. Now,
So the slope of the tangent line is 2.
the slope of the tangent line is 2. I'm going to tell you that there's a better way to do it than what I just did. And that's why this is thrown in the section project. See, what I did, I think is most understandable. That's why I like to start it. If you understand what you're really computing when you compute the slope of a tangent line, you basically get the slope of the secant lines and then move the points closer together, take the limit. That's understandable. But in terms of doing this efficiently, we want to learn about something called the derivative. And so that's what I'm trying to do here in these next couple slides. There's the slope of the tangent line. You ready? You see that right there? The way you read that is f prime of c. Okay? That little apostrophe, we're going to say prime. F prime of c. Now, you'll notice some things. And that is that formula is somewhat different than what we had before. We had limit as x approaches c, f of x minus f of c. Right? Well, let me do this. What do we have that's still the same? F prime. It's a little apostrophe. It's apostrophe. Yeah, actually, let me write it down with you guys, and maybe that'll help. So here is what we had the formula for the slope of the tangent line, right? So now the deal is I have some function f of x, right? So what I'm going to teach you now is called f prime of c. And the formula is this. Basically what I'm going to do, actually, I didn't have room. Shoot. Try again here. Instead of limit as x approaches c, what did I write? Do you remember?
Delta x minus 0.
Delta x approaches 0. Now that symbol delta, you may have seen it in a physics class. Do you know what it means? Change. So let me draw the picture on the side here. I had a function, remember this? And what I did was I wanted to come up with that slope of 2. So first I computed a slope of 3. But then what I did, see this is my, on the x-axis, this value here is c. This value here is x. So if I ask you, how far apart is, what's this distance here? Well, isn't that x minus c? Right? I mean, in our example, it was 2 minus 1. Remember? But another way to write that is just delta x. Matter of fact, when you do slopes, a lot of times we write change in y over change in x. We could just call that delta x. Does that make sense? Okay. And I kept this the same. The only thing that I've changed, other than that, is here in the formula I just wrote x plus delta x. And that might confuse some of you. Oh no, I didn't write x plus delta x. I wrote c plus delta x. Now why did I do that? Because if x minus c equals delta x, you just need to make one little algebra step. What does x equal? C plus delta x, right? Just add c to both sides. You guys see that? So this formula, I think, is very understandable as long as someone guides you through it. F prime of c. Are you with me on that? Now, what is this a formula for? The slope of the tangent line at the point, at where? At the point C. It only works at the point C. Now what was our C value? 1. Could you do this problem for a different C value?
Of course.
Sure. It doesn't matter what C value you use, that formula works. So now what I'm going to do is I'm going to take that C value and I'm going to replace the C's with X's. That is the derivative. Oh, one more thing I did, and this is very common. Delta x, again, I'm a lazy mathematician. Delta x is a lot to write, so what I write instead of delta x? H, and that's very common in a calculus book. We're going to write h instead of delta x. But what I have here is I have a function, and that function will give me the slope of the tangent line anywhere. Because you could put any number you want in for x. So it's f of x plus h minus f of x all over h.
Yeah. Isn't that kind of like the one from the first homework that we did?
It is, isn't it? On the first homework we did, they had you computing these big fractions, but the thing is, you didn't know how to do limits yet. So that's why, they were warming you up for this lesson.
What does H stand for, did you say?
H was the same as delta x. It's the change. It's the small change, right? And what are we doing? We're taking this small change, this delta x, or h, and we're making delta x go to 0. And that means I'm pushing the points together so that my secant lines look more and more like a tangent line. All right. So, let's go to an example. Here's a function, x to the 4th power. By the way, do you guys know what the graph of x to the 4th power looks like? Show me with your hands if you know. Oh, you guys don't know? Oh, wait, I'm seeing it. Where is it? It's kind of like x squared. Here, I'll show you. I thought you guys knew this one. What's y equals x squared looks like? Show me with your hands what y equals x squared looks like. All right, there it is. Well, x to the 4th is very similar.
More narrow.
It's more narrow, that's right, because when you take something to the 4th power, 1 to the 4th power is 1. 2 to the 4th power is already 16. So look, I'm off the map already when I do 2. Okay? Anyways, I like using this example for showing you how to compute the derivative. Okay? The derivative is going to be a function that will give me the slope of what? Tangent lines. And you can imagine what tangent lines might look like on this problem. Okay? So, let's do it on our paper. Okay, we're going to use that formula, and we're going to do an example. So my example is f of x equals x to the 4th power. Okay, and I'm ready now. I'm going to compute the derivative. It's called f prime of x. And again, let's just write down the, well, you have, I guess you guys just did write down the formula, right? So I'm going to show you something about how I compute it. I'm going to write down limit as h approaches 0. I like to fill in the denominator first because that's easy. H. The next thing I like to fill in, I like to fill in this f of x right after the negative sign. What am I going to write where it says f of x? X to the 4th. Okay. Over here, f of x plus h, do you know what I'm going to write?
The x to the 4th plus 0.
No? Good guess.
X plus h to the 4th.
X plus h to the 4th. See, what this means is everywhere that there used to be an x, you're going to put a what? X plus h. So that's what's being raised to the 4th power. Does that make sense to you guys?
Can you explain it again, please?
Yeah. When I say find f of 7, how do you do it if this is your function?
You plug in wherever.
You plug in 7. You do 7 to the 4th power, right? Whatever that is. Or if I say find, here, try this one, f of 3. What's that going to be? 3 to the 4th, what's that? 3 times 3 is 9, times 3 is 27, times 3 is 81. Okay?
Mm-hmm.
Now if I say f of x plus h, well, everywhere there used to say x, you put x plus h. So it's x plus h to the 4th.
Okay.
Okay? That's what that part means. I think that's the hardest part of this formula. That's why I do it last. You guys with me?
Mm-hmm.
All right. Now, by the way, if you were to plug in 0 right now for h, what would happen? What would happen? What would you get?
Indeterminate.
You would. You'd get 0 in the denominator, but you'd also get 0 where? In the numerator. Okay?
If we plug in 0
Yeah.
and we don't get 0 in the numerator,
Well, then there's an asymptote, right?
Yeah.
So then we have problems. Yeah, you won't be able to compute the
that
limit.
won't happen then.
Well, it
Well,
could, but then you won't be able to compute the limit.
you can just write that.
Matter of fact, we're going to learn that sometimes you can't compute a derivative.
Okay.
Okay? That's going to happen. You'd say it doesn't exist or I can't compute it. All right. So now what do? Now we expand x plus h to the 4th power. Do you guys know what that is? Oh, yeah? Okay. How about if I gave you this one instead? X plus h squared. Do you guys know what that is? If you say x squared plus h squared, I'm going to be really ticked. It's right. This means x plus h times x plus h. So when you square a binomial, you get a trinomial. What do you get? X squared plus 2xh plus h squared. Okay. So that's x plus h squared. So basically, if you took that and if you multiplied it by itself, right, you'd get it. That's the hard way. I should show you a shortcut. You want to see a shortcut?
Ah, you send that.
So this is actually really kind of cool. Here, before we do that, let's do x plus h to the 3rd power. So what do I do? Well, that means x plus h times x plus h squared, right? Which I just did. Okay, so this is x plus h times And I just worked out x plus h squared. It's x squared plus 2xh plus h squared. There it is. Okay, so I need to distribute the x and I need to distribute the h. But I don't really need to do that. You guys need to do that because we need to practice our algebra. So I will pause while you guys work out what that is. So if you were able to do all this correctly, x plus h to the third power equals x cubed plus 3x squared h plus 3xh squared plus h cubed, if you're able to do that correctly. And then, if you take that and multiply by x plus h, you'll get what x plus h to the fourth is. But that's the hard way. So I want to show you the easy way. All right? See, what you can do is you can look at a pattern here of coefficients. Let me show you what I mean. I'm looking at the numbers in front, and I'm seeing 1, 3, 3, and 1. Do you guys see that? Are you with me? Or here, when I did x plus h squared, the pattern of the coefficients in front is 1, 2, and 1. That was the coefficients of x plus h squared. This was the coefficients of x plus h cubed. You guys see that? How about, what if I had x plus h to the first power? What does that equal?
X plus h.
Right. So then it's just ones. Or what if you had x plus h to the 0 power?
It's 0.
Oh, careful.
It's 1.
Why? Anything to the 0 power is 1, but you're also talking about Pascal? What do you mean? Pascal's triangle. How many have learned this before? Well, use it. Right? So we get, the pattern is let's add, right? If I want to get that 3, that's 1 plus 2. So when I want to do x plus h to the fourth power, right? What are the coefficients going to be? 1, well, 1 over here, 4, because 1 plus 3 is 4. And then 6, and then 4, and then 1. So let me write down what that means. That means that x plus h to the fourth power is equal to, well, the 1 x to the fourth plus 4, what would it be? X to the third, and you're going to have an h also, yeah. Plus, see that the powers of x are going down and the powers of h are going up. What's next? Nice. 6x squared h squared plus 4x h to the third plus 1. H to the fourth. I should have known that. The first term had to be x to the fourth. The last term had to be h to the fourth. Now I'm ready to actually go back and do the problem. Wow. That's a lot of extra algebra that we need if we want to do this more quickly. I think it's worth seeing, though. I don't like just doing the easy stuff. Here, let me go ahead and work this one out on the next page, now that we have our little trick. Okay, so starting over, we had a function. F of x is x to the fourth. We had to compute the derivative. F prime of x, we said, is the limit as h approaches 0. And you guys have this, right? You have, it's x plus h to the fourth minus x to the fourth over h. And so what I'm telling you is, I can now fill in for that x plus h to the fourth, this stuff. What do I fill in? Well, it was x to the fourth plus 4x cubed h plus 6x squared h squared plus 4x h to the third plus h to the fourth. That's what that is. Minus x to the fourth.
How did you just figure out 6?
How'd I get the 6?
Yeah, with the, 'cause I saw the triangle, but now you got 4, 6, 4.
Oh, I'm sorry. I thought I explained it. When you have the triangle, you need to add. So like when we had 1, 2, 1, the reason that we get 1, 3, 3, 1 is because 1 plus 2 is 3. Or here, 1 plus 3 is 4. 3 plus 3 is 6. It's like the two numbers above in Pascal's triangle give you that one. Okay, so I could do the same thing. I could say, hey, what if you had a problem with x plus h to the fifth in it? You might imagine that. What would be the coefficients you'd want to use? See how I'm getting them? I'm taking the two numbers above. What's the next one going to be? 5, and then there'll be a 1. This is called Pascal's triangle. It's a nice little thing to see.
You said there's an easier way than this?
This is easier than...
Is there an easier way than this?
No, I think this is about as easy as we get.
Oh, okay.
Okay. What's that?
When you write it all out, there's a lot.
Oh, yeah. Well, you guys have to understand, you guys are in a calculus class, and these problems are going to take pages of paper. Please, don't try to, like, squeeze it all on 2 sheets. No. I mean, you're going to be stapling packets together. It's going to happen, you know? It'll be great. Anyways, let's go back to here. Okay. I'm still not done. I'm trying to compute the derivative. I got this big, ugly mess. Can we do anything here?
You can cancel out the x to the 4th minus x to the 4th on the top.
Oh, there's something at least. What's x to the 4th minus x to the 4th?
Nada.
Okay, so that goes away. So I get the limit as h approaches 0. And you mad slashers, I know, want to start canceling the h. But you have to be careful here. Because each one of these terms is being divided by h. Right? And so really, to do it accurately without making a mistake, again, I want to factor in the numerator. I'll factor an h out of the numerator. And what's left then? 4x cubed plus 6x squared h plus 4xh squared plus h to the 3rd. Right? Oh, I got a little sloppy there. Sorry about that. I'll clean it up on the next line. Why did I factor the h out? Because now I can cancel it. See that? H divided by h is 1. So I now have, this says, let me clean it up a little more neatly on this line. Limit as h goes to 0 of 4x cubed plus 6x squared h plus 4xh squared plus h cubed. You know, when Joe said that we did that in chapter 1, he's right. We did problems just like this, except for one thing. We didn't have a limit in front. But now we do. And so what do we say? What does this equal?
0.
Well, can I plug a 0 in for the h's? Yeah. We want to get the h out of here. You've been saying that for about an hour now, right? Anyways, when we plug in, we get 4x cubed. See, there's no h's there. Plus 0, plus 0, plus 0, right? So, what did I just learn? What the heck? Hey, this is what Mike's talking about. We did so much work, I can't even see what I was computing. Do you remember what I was computing?
Slope of the tangent line.
Well, not quite. I was computing what's called f prime of x, the derivative. So let me go through what we just did again. F prime of x is 4x cubed. So the original problem said f of x was x to the 4th. And what we just computed is f prime of x is 4x cubed. That's what happened. And I'm reminding you of that because now we want to use it. Yeah.
Can I ask you a quick question?
No. I might run out of time. I want to ask you a question. Can you do this? If f of x is x to the 4th, can you find an equation to a tangent line? Oh, that's an awful slide. Because I don't like what that says. It looks like it says 5,625. That's not what I mean, though. 5, comma, 625. Do you understand what I mean by that? No? Let me say it again. Here. On the calculator, can we see that point? Here, if I hit second, calculate a value, let me plug in a 5. It gives me an output of what? 625. That's ridiculous. I mean, think about where that is. You know? And again, you guys were telling me that you understand that this function grows more quickly than a parabola. It does. Like, here, the picture is this, guys. Like, you know, the thing shoots up, right? Well, way up here somewhere, the curve is going like this through the point 5, and then 625 is the output. You guys see that? Do you think the slope's going to be pretty steep up there? Yeah, I think so too. How steep will it be? Well, here's the thing. This new function, use the derivative to compute m tan anywhere. All right? That's the deal. So if I want to know how steep it is, for example, here's another tangent line right here. See that one? At the bottom of the curve right at the origin, do you know what the slope of that line is? 0, because it's horizontal. That's because f prime of 0 would be 4 times 0 cubed. 4 times 0 is 0. Okay? But what I'm supposed to do in my problem, I only have 5 minutes left, I'll get it done, is I want to find the equation of the tangent line through that point. Find the equation of that red tangent line. Okay, so the slope of the tangent line is going to be f prime of 5. Right? I don't know. Let me see. It's 4 times 5 cubed. So 4 times 125. Yes, it's 500. The slope is 500.
That was my question. I didn't know where we were going with the derivative.
Okay.
I thought I missed it.
No, I hadn't said yet. We spent so much time just computing it.
Yeah.
With those shortcuts. Don't worry. There are shortcuts. But that's what it does for me. It gives me the slope. Oh, and I didn't quite answer the question yet, because if you look at the question, here, let me put it back up there for you. It didn't say find an equation. Oh, it says find an equation of the tangent line, not just the slope. So you guys know how to write the equation of a line, right? What's the equation of a line that we usually use? Ah, there's one. So I remember what's called slope-intercept form.
Gotta put it down a little bit.
Okay. Slope-intercept form of a line was y equals mx plus b. So in my example, what can I fill in right now? I could fill in y equals 500x, right? You guys with me? I got the slope of that line. The only thing I didn't get yet is what?
B.
That y-intercept. That's a little harder to get. I want to remind you of another thing you did in algebra that's actually better here. It's called point-slope form. Does anyone remember this? What is it? Shout it out.
I'll try it.
Go ahead. Y minus,
Y minus Y1
yes, that's it.
is equal to m times the quantity x minus x1.
I find that this is easier. This is good if you know a point and you know the slope. We have the slope is 500. Do you remember the point that we have? Wasn't it 5 and then? Yeah, so this is my x1 and this is my y1. So let me use that. Y minus 625 is equal to 500 times x minus 5. That's the equation of the line. or n equation. Now, if you said to me, hey, Paul, put it in slope-intercept form, I could do that, right? I could say, okay, y minus 625, I'll distribute the 500. What's 500 times 5? I think it's 2,500, right? And now if I add 625 to both sides, I'll get 500x minus 1875. What a nice equation of a line. So if you go back to my picture of this thing, you know, I had this tangent line with a slope of 500, and it goes way down here through the point 0 and negative 1875. I got 2 minutes by my clock, but if you got to go, you can go. That's fine. Let me see. That's it for PowerPoint today, for sure, so that's good. I guess the point is, for any function I have, I can compute a new function called the derivative, and then I can use that function to find the slopes of tangent lines. Okay? And like I said, this is kind of an all-week thing, so we're going to play more with it on Wednesday. Nice work today, you guys. Yeah, it's on there on Blackboard. If you take a look, I updated Blackboard, and everyone but Christina can see it. So.